Hi, this is Alex from devstories.eu. Biopython Fundamentals, Episode 10 of 18. Proteins are often stored as a flat, one-dimensional string of letters, but they function in a complex three-dimensional reality. Mapping a 1D sequence to a 3D coordinate space requires a strict predictable hierarchy. Navigating 3D structures with Bio.PDB provides exactly that map. When you download a file from the protein databank, it comes as a massive block of text. Historically, this was the .pdb format. Today, the standard is the .cif format. Writing your own code to read these text blocks line by line is an exercise in managing edge cases. Bio.pdb solves this by converting the text into an object-oriented tree. To do this, you use either PDB parser or SMCRA parser. You create an instance of the parser, call its getStructure method, provide an arbitrary name for your structure, and pass in your file path. What you get back is a structure object. This structure object follows a strict data architecture known as SMCRA. That stands for Structure-Model-Chain-Residue-Atom. Every 3D file parsed by Biopython is organized into these 5 nested levels. The root level is the structure. A structure contains one or more models. If the protein was solved using X-ray crystallography, there is usually just one model. If it was solved using NMR, there might be dozens of models representing different structural fluctuations. Usually, you just grab the first one, which is located at index 0. Inside a model, you have chains. Many proteins are complexes made of multiple interacting polypeptide chains. These are typically labeled with single uppercase letters, like chain A and chain B. Inside a chain, you find residues. These are the individual amino acids that make up the sequence. This level also holds ligands and water molecules attached to that specific chain. Finally, inside a residue, you have atoms. Here is the key insight. You can navigate this entire tree using simple iteration or dictionary-style access. If you write a for loop over a chain, it yields residues. If you iterate over a residue, it yields atoms. If you know exactly what you are looking for, you can drill straight down without looping. If you need the spatial coordinates of the alpha carbon and the 100th residue of chain A, you just stack your lookups. You take your structure object, ask for model 0, then chain A, then residue 100, then the atom named CA. Consider a practical scenario. Extracting the 3D coordinates of all atoms in a single specific residue. First, you initialize your parser and load the file into a variable. Next, you isolate the target residue. You create a variable and assign it the result of looking up model 0, chain A, and residue 50 from your structure. Now you write a standard for loop. For each atom in the target residue, you request its coordinates. Biopython returns these as a NumPy array representing the exact X, Y, and Z positions in space. You print the atom name and its coordinate array. In just a few lines of code, you've bypassed thousands of lines of raw text and extracted the exact spatial data you need. The SMCRA hierarchy ensures that every atom in every structure file is found using the exact same logic. That is your lot for this one. Catch you next time.